So now I would like to welcome all of you, the attendees, and especially our guests, Dr. Nacer Chahat from NASA JPL for today's webinar. And also I would like to welcome all the participants first of all. So this particular webinar, for this particular webinar, we have received more than 230 registrations from actually 20 different countries. Out of that, some of the countries are like China, Canada, USA, Myanmar, Saudi Arabia, Algeria, Malaysia, United Kingdoms, Iran, Spain, Greece, and Switzerland. These are some of the major countries from where we have received registrations. Now, I would like to say a few words about Dr. Nacer. So Nacer is basically from France, and he have about more than 10 years of experience in the field of development of antenna projects for from UHF to terahertz frequency, especially having radar and imaging systems. So his expertise includes some key satellite antenna designs, and he had executed many NASA JPL operations such as spacecraft for CubeSat, landers, rovers, and many such kind of operations which was associated with NASA JPL. So he worked on several flight projects such as Europa Clipper, Mars 2020, Mission Suit, and NISR, Marco mission, and lunar flashlight, RAINCUBE, and many other such kind of missions of NASA. So he have a very vast experience in his area, and we are pretty sure that today we are going to explore lots of possibilities of research and lots of emphasis on what kind of research, especially in the field of CubeSats and such kind of antenna fields design can be processed. So this is our pleasure to have on board with Dr. Nacer. Now, just going ahead with the formal process to inaugurate this webinar. Now, I would like to invite MTT-S SBC Chair, Professor Dr. Kusman Nasorov. If he is here, then have a few words for a minute. So now, Saurabh sir, if you can have a few words for a minute, please.
Thanks, Amit sir. So on behalf of IEEE MTT Student Branch Chapter IIT Jammu, I welcome the speaker and all the participants for the today's event. So the IEEE MTTS Student Branch at IIT Jammu is a 1 year old body at IIT Jammu, but the branch is very active in the current pandemic situation, and we are regularly organizing workshop and talks. So it is our privilege to have for today's talk Dr. Nacer Chahat, and Amit has already mentioned many things about him, and he is mainly working in the spacecraft antennas, and he in the today's presentation is based on the spacecraft antenna for NASA Deep Space and Earth Science mission. So we all are delighted to listen for the today's presentations, which will give us a brief understanding of what the things and what are the means antenna related parts is mainly going in the NASA space mission. So with this word, I request Dr. Amit sir to again continue with the today's event, and
Okay.
so it's really a matter of big privilege that we are having a scientist from NASA to give a talk for in our IEEE MTT Student Branch Chapter of IIT Jammu. Thank you, sir.
So now I would like to invite IEEE SPC Dean, Professor Badri Subudhi, to have few words if he can. So Badri sir, please, just for a minute. Yeah, Badri sir. Looks like some technical problem. So maybe we will go ahead with our head of the department, Professor Ankit Dubey, to have few words with him. So now I would like to invite Dr. Ankit Dubey to have few words. So over to Ankit, sir.
Thank you, Dr. Amit, for inviting and organizing such a nice event. And I would like to congratulate the MTT-S Society at IIT Jammu and IEEE student branch of IIT Jammu. And they are very active during this pandemic situation. Although the institute is closed, students are at home, but they are regularly organizing such a nice event. And in this, the same line, initially we organized an talk where we had a scientist from ISRO, and now we have a scientist from NASA as well. So basically, it is taking our event from local to global, and it is giving a flavor of the global touch as well, because we have now 20 participants from 20 countries, which is a huge. It's a that, that itself shows how impactful these events are. And I'm really happy that Dr. Nacer Chahat has agreed to deliver a nice lecture here, that too on satellite antennas. And in fact, I would like to just add that our team at IIT Jammu is actively working on designing and development of a cube satellite, and also we would like to take it forward. So uh, if there is a potential for collaboration, we are open for it. And I would like to congratulate Dr. Amit and his team, entire team of IIT Jammu, for organizing this event. And I would like to welcome all the participants. And I hope this will be an entertaining and as well as infotainment session for you. And I hope that this will also encourage all the participants to work towards this space technology. So those who are very enthusiastic to work on this, and those who are really interested, they can be connected with us through this after this event as well. So I would like to again thank Dr. Amit and the speaker, Dr. Dr. Chahat, who has agreed to come here. And now I would like to hand over the control again to Dr. Amit to continue this event. And yes, welcome all. Welcome once again from IIT Jammu Electrical Department.
Thank you, Ankit sir, for this. And now, coming back to you, Dr. Nasir. So, whenever I meet to you, the last time it was in CAP in Ahmedabad, I think we spent about 2 3 days there quite simultaneously together. And whenever we were discussing those facts, it always they are always memorable for me as well. So now this is over to you, and the dais is yours. Now you can discuss whatever you want to have. So welcome, Nasir. Please go ahead. I think your Nasir mic is muted. Your mic is muted. Yeah.
Okay,
Now
can
this
you
is
hear me now?
over to you, and the dais is yours. Now you can discuss whatever you want to have. So
Okay,
welcome. Please go ahead.
so thank you for the nice introduction, and thank you for inviting me here. It's my pleasure and my honor to give a talk. So I'm very glad that the IEEE student branch chapter of IIT Jammu is very active, and like I said, I'm very happy to participate and share the knowledge that we have accumulated. So thank you for the nice introduction, and thank you for inviting me here. It's my pleasure and my honor to give a talk.
We are getting echoes. Is it?
Yeah, I don't know why. 1 second.
Oh, no, now is it fine?
Is there still an echo now?
Yeah, yeah. I think you can start. Looks fine.
Okay. Okay, so today I will be talking about spacecraft antennas for deep space and Earth science missions, and I will go over a very, very wide spectrum of technologies that we've developed at JPL. Some have flown successfully, and others are just technology in development, so that you have an idea of what we are doing. We're always trying to look forward for future missions, so we always focus at least 20 to 30% of our time on technology development. to make sure that the future missions will be able to enjoy better technologies and that will be able to enable better instruments, science instruments. So I will start with one that most people who are involved in space are very familiar with. So the first one is MARS-CUBE 1, also known as MARCO. This is a small satellite, 6U CubeSat, which is 10 by 20 by 30 centimeter. So it's basically the size of a shoebox that has flown to Mars along with the lander called InSight. So the objective of InSight was to land on the surface of Mars. It's a lander, so it's a static robot. And once InSight lands on the surface of Mars, it will carry on his science investigation. So my contribution to this mission was to develop the antennas on the CubeSat that will relay in real time the entry, descent, and landing data as InSight is landing on the surface of Mars. The reason why we sent CubeSat along with InSight is because we wanted to be able to relay data and perform a band-pipe communication to enable real-time communication. So as InSight will land, we will be receiving the data on Earth. If we were not able to have this CubeSat, we would have gotten this information several hours after, because the Mars orbiter would have been hidden behind Mars, so there would be no line of sight. So we wanted to avoid that, and we wanted to get in real time the data. So we sent 2 CubeSats. The reason why we sent 2 CubeSats is to increase the chance of success. So obviously, the likelihood of a success with 1 CubeSat is not as good as the likelihood of having 2. So the statistic was about 99% of success rate using 2 CubeSats. So that's the reason why we did that. And one needs to understand that making 1 or 2 CubeSat is not a significant amount of money difference. So that's also the reason why we were able to fabricate 2. So if you develop large satellites, if you go from 1 to 2, the price of the mission will go quite significantly. For CubeSat, it's not quite the same. So the photography that you have on the left is actually described very well what we try to attempt. We would have the 2 CubeSat flying by Mars. So we're not orbiting around Mars. We are only flying by as InSight is going into his entry, descent, and landing phase. InSight will transmit the data to the CubeSat through UHF around 400 megahertz. And as the CubeSat is receiving this data, is transmitting back to Earth at X-band in real time. So as we are receiving, we are transmitting with the same data rate. That's what we call a band-pipe communication. So it was not a straightforward achievement, because we had to find a way to have an antenna that was 3 times the size of the CubeSat, and yet not using any storage volume inside of the CubeSat, because all of this volume was taken by the spacecraft itself. So that's why we came up with this reflector array technology that folds atop of the surface of the CubeSat bus and deploys, as you can see on the left video. So we have 3 panels that are deploying with spring-loaded hinges. So that's the simplest deployment that you can come up with. It's completely passive. It's held in place. It's held in place against the CubeSat bus with a burn wire. And as we apply current to this burn wire, the wire cuts. So hence the name of burn wire. It burns the wire, and the entire reflector panel deploys, releases. And we also have the feed, which illuminates the reflector array, which is also folded against the CubeSat bus. Nothing, as the panel deploys, then the feed releases. So we needed to achieve about 28 dBi gain. How did we come up with these numbers? It's pretty straightforward. We needed about 8 kilobits per second data rates. And we knew that we could not have more than 5 watts output power from the SSPA. And so those are the constraints that we have. So then you do very simple math based on the area of the antenna and knowing what type of efficiency you could achieve. We knew that we needed about 3 times the size of the CubeSat bus. So this here, what I wanted to show was actually the optics of the reflector array. So you can see the feed is located here and illuminates the reflector array. And then we have a pointing angle of about 23 degrees off the bus and the reflector array surface. So those are the constraints that we have. And we had these constraints because on the bottom, we have a UHF antenna that I will be talking about as well, which is receiving from inside. So that's why we picked this angle of 23 degrees. So when you design a reflector antenna or reflector array antenna, you always start with an ideal directivity, which is given by the area of the antenna itself. Then you know what losses you will have. You will have taper and spillover losses due to the illumination of the feed. Then you will have feed loss in this case. And you will also have ohmic losses from the reflector itself and dielectric losses as well. So those are the things that you see in this table. You also have hinges that take some area of the entire area of the reflector array that will also contribute to losses. And you have small gaps between the reflector as well that you need to take into account. And on top of that, you will also have a thermal deformation of the panel, surface RMS of the reflector array panel, and also misalignment due to the hinges deployment. So if you cannot expect that the reflector array will deploy perfectly, so those are the things that we had to work with. We developed hinges to avoid having gaps between the panels. We developed these hinges also to develop very accurately in a very reproducible way. And we also developed the reflector array technology to be resistant against thermal gradient across the surface of the reflector array. So all of those are things that we had to assess very accurately to make sure that we will get about 28 dBi out of this reflector array. One of the critical things that we needed to be very careful with was actually the design of the feed. The reflector array design is actually pretty straightforward. Any antenna engineers can design a reflector array like that in a very, very trivial way. It's not an effort that takes a lot of time. And there is very little room to make mistake with the design of the reflector array as well. But designing a feed to maximize the efficiency of the antenna is very tricky, especially because the feed is what provides the circular polarization, which is obviously required to communicate with Earth. So so here you can actually see the overall radiation pattern of the reflector array, measured and calculated. So you can see that we had very, very good accuracy. We achieved a much greater gain, more than 29 dB. So we were very happy with these results. So now I'm going to focus a little bit more on the feed. So let me go back actually. So if you look at the optics, you can see that the feed is going to illuminate the reflector array, but very close to the feed, there is the bus. So when we design the feed, you have to be very careful with that. And the reason is very simple. when you're going to illuminate the reflector ray, you will also have spillover, and some of the power will be going toward the bus. And the power going toward the bus will reflect and will then bounce toward the reflector ray, and that will cause your radiation pattern to be distorted. So you have to mitigate the power radiating toward the bus. So as a result, we used, so first we used a 2x4 feed element, but we also applied Taylor tapering to make sure that the side lobe level will be minimized as much as possible towards the bus. And there is also a trick that I applied to have the side lobe level even lower toward the side of the bus. So as you can see, there is an asymmetry, and we have about almost 5 dB lower toward the bus. So we almost achieved 25 dB of side lobe level toward the bus. And so we were completely resistant against any interference from reflection coming from the bus. And those are the radiation patterns that we got from the feed. As you can see, the accuracy between calculation and measurement is quite outstanding. You can see on the right side, top right side, the feed power divider, and you can clearly see how we achieved the tapering, where we have more power in the inside and less power on the outside patch elements. And on the feed, one key technology that we implemented, if I can say technology, we actually used a GPO connector because we had a very, very tight schedule and we didn't have time to design a connector, a rotary joint at this frequency band that is that small. So we decided to rely on a GPO, which is a pushing connector. And that allows you to have these rotation features, even though it's not developed to do that. And it worked out really, really well. So sometimes you have to be clever by using existing technology for things that are not meant to be useful. Okay, and then on the other side of the CubeSat, we have a UHF antenna. And I wanted to discuss about that because I think it's a very, very good example of a good, smart engineering. This antenna was actually not designed by myself. It was designed by my friend, Emmanuel de Crosas. So the clever thing about it is how he achieved circular polarization. So most of you are probably familiar with loop antenna. Loop antennas are meant to be used as a linear polarization antenna. So if you excite the loop antenna on one corner, the loop dimension is about lambda. You excite it on one corner of the antenna, and you get linear polarization. And as you can see here, the arrow shows you where the linear polarization is oriented. So if you go on another corner, you get the polarization on the other side. But that explains to you how you can play with the fitting of a loop to get different linear polarization orientation. So then if you put the loop antenna on the CubeSat, you can actually have an antenna that is more directive because you use the CubeSat as a reflective surface. Quite simple, as long as you maintain a good distance between the right distance between the loop and the CubeSat itself. So you have to deploy the loop at the height, at the right height. So then, most antenna engineers or RF microwave engineers know that to obtain a circular polarization, you need several things. The first thing is that you need to excite two linear polarization. And this linear polarization needs to be orthogonally excited. And you also need to have a 90-degree phase difference between this polarization. So here I actually show on the bottom that if you excite on the bottom left corner, you will get one linear polarization. If you excite on the right bottom corner, you you will excite an orthogonally linear polarization. And then if you apply 0 to 90 phase difference excitements, you get left-handed circular polarization. And if you change from 0 to minus 90, you get a right-handed circular polarization. So that's the trick. And although that seems pretty trivial, after I explain it, it's always pretty clever to find a solution like that. So then the next step was to find a way to actually excite these two feeding points with 90 degrees out of phase. And what we did is that we actually used a balloon that used the loop as a ground plane. And that's what you can see here. So the loop is on the other side, and the power divider balloon excite on one point here and on the other side here. And with the phase difference, you get 0 to 90 phase difference between the two. So that part is quite trivial as well. But exciting, relying on the loop as a ground plane to develop this power divider is also another clever way to achieve that. And then for the deployment, what did we do? We used a very simple way to do that. We have spring-loaded hinges that deploy this antenna off the surface of the CubeSat, like a jack. I forgot how you call that. Never mind. So you deploy that in a very simple way, and we also have these cables that are transparent, RF-wise, that holds the antenna in place so that it stops vibrating, and it holds it in a very reproducible way as well. Okay, so then the next step was, once we fabricated this antenna, measure it, and as you can see, because we're very low, at a very, very low frequency, you cannot do an indoor measurement, so we had to use the outdoor range. And you can see on the top the CubeSat mockup, where we have the UHF antenna, and on the other side we have the receiving antenna to perform this radiation pattern measurement. And here you have the calculation and measured result, and we have error bar around the measurement, because obviously these measurements are not as reliable as high frequency measurement that we do at X band or K band or even higher. So that's one thing you need to know, is that when you do measurement at UHF, outdoor measurement, you have to be aware of the error bar that come with it. Okay, and then here I wanted to show you several things. So first, on the left is a picture that the CubeSat actually took on its way to Mars. So on this picture, you can see Mars on the background, and you can also see the reflector panel on the top and the feed on the bottom. And the reason why we had a camera to do that was to verify that we deployed the reflector panel and the feed in the right position. So we took the exact same pictures on the lab, and then we overlapped these two pictures to verify that things deployed as predicted. So we successfully deployed the two antennas. The two CubeSats survived the trip to Mars. They both relayed the data. We did some calculation, link budget calculation, that demonstrated that the gain was within plus minus 0.4 dB, which is quite outstanding. And we also verified the radiation pattern in space as right after we released right after we deployed the reflector and the UHF antenna. So that's one of the first things that we do during operations, is verify that the radiation pattern near Earth are as expected, because near Earth it's much easier to actually perform this radiation pattern measurement in space. But it's also the right moment to do it because you don't want to do that at the last minute, obviously. So here, what you see, the plot that I'm showing are actually the received power in the DSN, the Deep Space Network antenna. and in orange is actually Marco A, and in blue it's Marco B. So there is a difference between the two, and that's explained by the alignment between the ground station antenna and the spacecraft. So the way we are actually receiving data from the CubeSat, we have a single antenna that is receiving at the same time from the two CubeSats. The two CubeSats uses two different center frequencies, and the Deep Space Network antenna is capable of getting the data from a single antenna at the same time. But obviously, one of the two will not be aligned perfectly, and that's what explains the difference in receive power. Different thing that I show is actually the critical step of EDL, where you can see the parachute deployment and the lander touchdown. And then when the UHF link is over. So let's see, is there anything I wanted to say here? No, that's all. But so this data that we have here is what we actually use to check the gain of the antenna during EDL. And as you can see, we actually retransmitted as well with Marco B. So we did two passes. Since the CubeSat had the ability to record the data, we transmitted it in real time, and then we had a second pass where we transmitted again. Okay, so then following the success of Marco, we've been developing a lot of deployable reflectory antenna. For Earth science, people wanted larger aperture, larger directivity. So we went with an antenna that relied on Marco heritage, where we, instead of deploying only 3 reflectory panels, we now deployed 6 on each side. We made them fold in a very, very compact fashion, much more compact than Marco, where there was absolutely no gap between the reflectory. And we managed to do that very successfully. So this antenna is linearly polarized. It's about almost 1 meter by 80 centimeters. And we have a total of 14 deployable panels. On the back of these reflectory panels, we can also have solar arrays if we needed to. And here you can actually see the gain table. So like we did for the Marco antenna, that's always how we get to the final gain. We start with the ideal directivity, which is given by the area of the antenna, the aperture of the antenna. Then we have spillover and taper loss. We have the blockage in this case, since this is a Cassegrain antenna, so the subreflector is contributing to blockage. We also have losses due to the strut that holds the subreflector in place. We have gap losses between the reflectory panel, and again, losses coming from dielectric and ohmic losses of the reflectory. Surface accuracy, so surface RMS, feed loss, and feed mismatch, obviously. And here is a picture of the prototype. As you can see, it's a very, very pretty antenna. The feed is in the center, illuminating the subreflector, and the subreflector illuminates all of the reflectory panel. And the reflectory panels are designed to achieve the maximum directivity and gain. As you can see, we have a lot of cutouts that on the reflectory panel that we didn't have on the Marco design. And that's a very simple explanation behind that. We needed much better accuracy for the deployment at K-band. And as a result, we have bulkier hinges that have hard stops, and they take much more volume. So as a result, we had cutouts in the panel to make sure that we can accommodate the volume of these hinges. And as you can see, again, the calculation and measure results are in good agreement as well, despite the fact that we're operating at 36 gigahertz. Okay, now I'm going to talk about RAINCUBE. So RAINCUBE was the first active radar on a CubeSat. So RAINCUBE objective was to do rain and snow precipitation measurements. It is a nadir pointed radar. So they needed about 42 dBi of gain. So we need at least a half a meter diameter to achieve this gain. This antenna operates with a linear polarization. Again, that comes from the science. They only need linear polarization. So with a half a meter antenna, we need to achieve more than 50% efficiency to get the gain that we need. And we had about 1.5 U of storage volume inside of the 6U CubeSat. So 1.5 U correspond to 10 by 10 by 15 centimeters. So as you can see, when the antenna is folded, everything is very, very compact. So we have a telescoping waveguide that never moves, stay in place in blue here. Then we have the feed horn, which is in yellow, that telescope upward along the waveguide. And we also have the ribs in brown that folds around the horn. And the ribs cannot take too much space, obviously, to fit within the volume. So that contributes to the trade-off of the F over D of the antenna. So if the antenna F over D is large, then the ribs will be, the curvature of the ribs will be much smaller, so they will take less space. But then the feed horn, the focal point will be much larger, and as a result, you will have to have multiple deployments to get the subreflector and the feed where you need it. And we try to avoid that as well. Then, if you try to get the focal point closer to the reflector, you will have an F over D that is much smaller. But if you have an F over D that is much smaller, then the curvature of the ribs will be much more significant, and they will take much more storage volume. So there is a trade-off that you have there where you're trying to minimize fit within the volume that is allocated to you, but at the same time minimize the risk of failure during the deployments. And that's why we use a Cassegrain antenna that allows you to have the subreflector lower than the focal point and minimize the number of deployment of the feed. So let me show you a video of the deployment. So we have a four screws system that drive the deployment of the ribs and the feed horn. So up to now, as you can see, there is a very good control. And as soon as we get to the mid hinges of the ribs, there is no way to come back. So then you have absolutely no control, no way to come back. If something gets stuck, it's stuck. It's very difficult for you to do anything to fix it. Then let me show you again. You will see that the feed horn is completely pushed out, and the last step is the release of the subreflector. And once all the ribs are released, this is when that happens. And that's happening with a spring loaded that you can see in the center. Again, that's something that we don't control. It's completely passive. So there is no controller that allows you to deploy that or bring it back afterwards. So you need to be aware of that. And all of these decisions were made to minimize the risk of failure during the deployment. We try to keep it as simple as possible. And again, that was a very successful deployment in space. Let me show you a little bit details on how we actually designed antenna. So first we use the software TCRA Grasp. So as you can see, the feed horn here, the strut and the subreflector is a method of moment element. And we calculate that using method of moments, and we calculate the current on the surface of the reflector using PO, physical optics. And the surface of the reflector is represented using a Gore surface. So obviously, since we have a certain number of ribs, we have a number 30 ribs. Of course, there was also a trade-off. 30, ideally you want more to have a perfect parabolic shape, but then you will probably fail during the deployment because something will get stuck. So a good trade-off from RF and mechanical was 30. If you had less than 30, then at K-band, it would be very, very difficult to compensate for the surface aberration coming from it. Because even though the ribs are perfectly parabolic, the shape of the reflector between each ribs is flat between these ribs. So you don't have a perfect parabola there. And as a result, you have to compensate for the surface aberration by correcting for the focal distance of your feed and subreflector. So that's the number one thing to do. And using 30 ribs, we managed to bring back this loss coming from the surface aberration to almost 0 dBi. And that's what I'm showing here in this sketch. So you can see if you do not correct for the surface aberration coming from the Gore surface, then you will have an unfocused radiation pattern. So if you correct for the focal point of this Gore surface, you can refocus the radiation pattern. Yeah, and those plots in the bottom are actually measurements that were made directly out of the surface of this fabricated and deployed antenna. So we used some laser technology that allows us to measure the surface of the mesh without touching the mesh. So that's really what you want to do, so you don't interfere with the flight hardware, and you can get this surface, and you can put this surface into your model. And then you can verify what's the impact of the actual deployed surface. So in our case, we achieved more than 56% efficiency, which is really, really good. Actually, if you look at non-deployable antenna, commercially available non-deployable Cassegrain antenna, you will see that they are not achieving much more than that. So it's quite outstanding performance out of the deployable antenna. One more thing that I should point out here is that we used 40 opening per inch mesh, which is very, very dense mesh. This is also the first time ever we have used such a dense mesh in space. And that was to maximize the efficiency at K-band. And here is a video of the deployment of the antenna in space. So as you can see, same as Marco, we actually took these pictures to compare with the deployment in the lab, and we overlapped the two to verify that the ribs that we can see, obviously we cannot see all of them, are deployed properly. The subreflector that you can see here, and the three struts deployed properly as well, and the feed that you can see in the bottom. See one more time the deployment. Here we go. So everything went well. We were very happy with the deployment of the antenna, and once we verified that the deployment was successful, we could begin the commissioning of the instrument, the radar instrument. And here is one science plot that I really like that I wanted to show. This measurement was actually taken from two different CubeSats that flew over this Trami typhoon. That's the name of the typhoon, 5 minutes apart. So the one where you see the plot vertically is actually coming from our RAINCUBE CubeSats. And the one in 2D that you see in the bottom came from a passive CubeSat, also from the Jet Propulsion Laboratory. And this passive measurement is a radiometer. So it's basically looking at the temperature that it's seeing at different frequencies. And the scientists were actually stunned to see the agreement that they obtained from two different tiny satellites like that. And that's when people realized that you could actually achieve very good science using CubeSat. So let me just give you a little bit of background of why us at NASA Jet Propulsion Laboratory, we were very excited about looking for CubeSats to carry on Earth science experiments. The reason is very simple. There is phenomenon such as typhoon where we don't have the ability to look at a very, very fine temporal resolution with large spacecraft. And this is really where small satellites like CubeSat can be very helpful, because you could fabricate 5, 6, or maybe 10 satellites that are following each other that will give you this temporal resolution at very low cost, at an affordable cost. And this is where CubeSat can be very, very helpful moving forward. They could do science that large satellites will not be able to do, because you cannot fly 5 large satellites that cost 500 million, for example. So this is where small satellites are very helpful. And not only CubeSats can be done by large agencies such as ISRO or NASA or ESA or JAXA, but they can also be done by universities. And that's why we really would like to see more universities develop their own CubeSat to do science like that. So obviously, like I said earlier, the approach that we have at NASA is whenever we develop an instrument successfully, the scientists are also looking to improve the next satellites. And they always ask for more, which is great because it keeps us busy and it keeps us looking for the next technologies that will allow to get better science. So one thing that people were looking for was for deep space communication, having higher directivity and gain. So we worked with a small company called Tendeg to develop this deployable mesh reflector, which is 1 meter deployable mesh reflector that could possibly be scaled to even larger diameter if you went from CubeSat to small satellites. On a small satellite, we could use the same mesh reflector up to 3 meters. On a CubeSat, since we are constrained in terms of storage volume, if you use a 12U CubeSat, you will be able to have a 1 meter deployable aperture mesh reflector. And as you can see in the bottom, how this mesh reflector deploys. So this is a very, very good technology to have. So what we did was to design a feed at X-band and K-band, and we obtained more than 60% efficiency with such a reflector. So this is the X-band patch array that illuminates this reflector, and on the right, the K-band one with its polarizer. And you can see the grasp model for this one, where you have the CubeSat bus, the boom that holds the reflector at the desired position relative to the CubeSat bus, and you have the feed, which remains fixed on the CubeSat bus. And you can also see a picture here where you can see the X-band feed, the reflector, the mesh reflector, and the CubeSat bus. So as you can see, 6U is twice, 12U is twice the size of a 6U CubeSat. So we're now talking about 20 by 20 by 30 centimeter size. So let's look at some of the measurement results, uplink and downlink. So uplink for the deep space network is 7.2 gigahertz and downlink is 8.4 gigahertz. The efficiency we obtain is 68% at uplink and 64% at downlink, which is quite outstanding. And at K-band, we obtain about more than 50% efficiency. And again, as you can see, the accuracy between measurement and calculation is quite good. And then moving forward, again, like I said, we're always looking for the next instruments. The scientists were interested in using a small satellite and fly a larger reflector. This one is 1.6 meter. And we had a very, very clever idea of having 5 feet that are all collocated, and we could take advantage of the displacement of the spacecraft. So as the spacecraft move forward, so as you can see, for example, try to follow me here because it's not that trivial. So the feed 1, 2, and 4 will give you this pattern, 1, 2, and 4. And the feed 3 and 5 will give you these 2. So they can give you a 3 dB overlap if you take advantage of the displacement of the satellite itself. So on the right is what I'm actually showing. So you can see how you are getting almost 3 dB pattern overlap by taking advantage of the displacement of the satellite. So that's what we try to do here. We are obtaining at K-band more than 70% efficiency, accounting for all the loss, surface RMS, mesh OPI, and of course, spillover and taper of the feed. As you can see, on this model, we have the bus of the small satellite. We also have the solar arrays, and we also have the boom and the mesh reflector. So one thing I wanted to say here is, remember the great science I show you right here? So I told you about 2 instruments, RAINCUBE and Tempest-D. So you can look them up on internet. And this small satellite will actually fly, if selected, that's a mission concept, will actually fly the RAINCUBE and the Tempest-D on the same small satellite. And they will be able to collect the data that I was showing you earlier. So you can see one CubeSat demonstrated the technology, allowed us to improve the technology readiness level to TRL9. You can look up how they are defined. And because of that, we can now propose a small satellite concept that will allow us to get even better science. So this is how we proceed. And this is how we make progress and improve the science that the scientists can use to improve their forecasts. Now I'm going to talk about a new type of antennas, which are called metasurface antennas. So in the space world, this is a very, very new technology. They have never been flown, ever. Barely looked at. ESA has done some work on metasurface antennas, mainly for telecommunication. NASA has never worked on that until we started working on this. And I will show you some of the cool things that we came up with as a team. So the first one was actually a W-band antenna, which relied on a pillbox technology and metasurface technology to get multiple beam out of a flat antenna. So the way a pillbox works is very simple. So you have 2 layers. On the bottom layer is you have a spherical wave. So you can see that on the plot on the bottom. Can you actually see my cursor when I move it? And make sure that you guys can follow that. So you have different feed on the bottom layer. If you excite the feed in the center, you eliminate the reflector, as you can see here, with minus 10 dB H taper or so. And then you have a coupling slots between the bottom layer and the top layer that allows you to couple this wave to the top layer. On the top layer, you still have a reflector, and then the wave propagates with a planar phase front, which allows you to excite the metasurface elements. And then the metasurface elements that are located on the top layer will radiate and will radiate the way you want it. And in that case, we wanted a very directive antenna. And if you excite one of the horn that is located, which is offset, you can steer the beam on other directions. So here, the center one gives you 0 degree pointing, and the two offset antennas give you plus minus 45 degrees. And this is what the scientists were interested in. And you can do all of that with a very flat antennas, which is really where that becomes very attractive. Let me show you some of the measurements that we collected. So you can actually see the prototype on the left. Top left, you can see we have 3 ports that excite each of the feed, as I mentioned. And on the bottom left, you can actually see the metasurface. So this is called a holographic metasurface. And here, the spacing is picked to get a specific pointing in the E-plane. So you can play with the metasurface element to get different pointing in the E-plane direction. So you can see if you excite port 1, you're getting 31.9 dBi directivity. And you can see the pointing on the E-plane and the H-plane. Now, if we go on port 2, you can see that now we're pointing at 45 degrees, and that's exactly what we wanted to do. So as I said, we wanted to get plus minus 45 degrees on each side, and that's what the scientists are interested in to make some Doppler measurement to get information on the wind direction, for example. And as you can see, calculation and measurement are good. You can see that the side lobe level are getting a little bit higher than what we predicted, and that's due to a misalignment between the bottom and the top layer. That can be improved, obviously. And then I'm going to show you another type of metasurface. So this one was actually developed by my friend David Gonzalez, who's now working in France at University of Rennes for CNRS. So we've been collaborating on this technology for quite several years. He was a postdoc at JPL at the time when we initiated this effort. So we wanted to get rid of the dielectric, and we wanted a metasurface that was completely in metal. And that's what you can see here. So here you excite the metasurface in the center, and you actually modulate this surface wave that is excited by the feed located in the center to get a directive pattern. The beauty of this is that you don't need a polarizer to get circular polarization, because the metasurface is getting you this, is generating the circular polarization. So that also saves a lot of volume inside because you don't need a polarizer. So let me show you some of the measurements, and you can see a zoom in on the metasurface so you can see how they look like. I'm going to surprise you in a few minutes because I did not mention how we fabricate this antenna, and that's really key. So let's focus on the measurement results. So you can see the gain here, plot. So you get a pretty good bandwidth out of this antenna, and the efficiency can be as high as 50%. So now these metasurface antenna are not competing with, technologies we were using before, such as reflector and reflector. And as you can see, we get very good agreement between calculated and measurement, because we managed to develop a very good fabrication method for these antennas, which was really the key here. Let's look at it. So this is the fabrication method. So we're actually doing 3D printing. And you can see the speed to actually fabricate these antennas, which is really, really fast. And as a result, you can fabricate this antenna at a very, very low cost, and you can fabricate a lot of these antennas very quickly. So for small satellite or or CubeSat that's very, very attractive. And moving forward, we actually developed a new Metasurface, which is similar to the first one that I showed, entirely made of metal, operating at Ku band at 15 gigahertz or so. And here we actually get two beams with 3D overlap with a very good isolation, about 20 dB isolation, which you wouldn't be able to do with any other technologies. One beam is used for transmit, the other beam is used for receive. Then my friend Adrian Tang, who's a CMOS designer, has developed a CMOS system-on-chip radar that has a canceling technique that allows us to improve this oscillation down from 20 dB coming from the passive antenna to more than 50 dB isolation using his technique. So keep an eye on that. We will probably share some results very soon, but I wanted to show you what kind of things we can do using these technologies. I think I'm running out of time, so I'm going to go a little bit faster. Might skip some of the slides if you're asking me to finish. So please don't hesitate.
Nacer, you can continue, no problem.
Okay, great. So now I'm going to talk about one mission concept that I cherish the most, which is Europa Lander. We would like to go to Europa because Europa is a moon of Jupiter, by the way, icy moon of Jupiter, where we think that the likelihood of finding life in the solar system is the highest. And the best way to actually demonstrate that is to do an in situ measurements, meaning that we need to land on the surface of Europa and we need to take some samples and perform some measurements and send them back to Earth. The difficulty is that the conditions on the Europa surface are extremely severe for hardware, electronics, and also even for passive hardware such as antennas, which are located on the outside of the vault. So most of the electronics is inside of the vault to protect them from the high radiation levels. And that's really what the issue is. The radiation levels on the Europa surface are extremely high, which will only allow us to operate from 30 to 40 days. So we need to be extremely efficient in relaying all the science data back to Earth within this time frame. And not only the radiation level are very high, we also have cryogenic temperature. So the temperature are extremely high. The antenna are going to see temperature around minus 170 Celsius while operating. And to make this mission affordable, we needed to be able to transmit data back to Earth without a relay orbiter. And that's something that we thought was impossible from Europa. And we managed to enable that by developing an antenna that was extremely efficient, more than 80% efficient, that would not take any volume or very limited volume. So we could not use a reflector antenna, for example, because it would take too much space. So we developed this technology that's completely flat, provides circular polarization at uplink and downlink with more than 80% efficiency. And I'll show you a little bit details on that. This is what the antenna looks like. And as you can see, the antenna is all made of metal. And I will tell you a little bit more of how we actually survived the radiation levels. But first, I'll show you some of the results. So the first thing that we did was fabricate a subarrays, 8x8 patch elements, and demonstrate that the RF performed as expected. So as you can see, the calculated and measured results were very good. We got more than 80% at uplink and downlink. And comparing this performance to previous antenna technology that we've flown in the past, we are exceeding far beyond the performance that we obtained before. So if you look at this work, as I said, more than 80% efficiency. The antenna on MER was 25 and 49% efficiency. The antenna on MSL, so Curiosity, was around 49 and 44 efficiency. And this antenna, which was this one, the radial line slot array, was the original baseline of the lander. And this one was even worse. So the reason why it was the baseline was that it was the only all-metal circularly polarized antenna that was proposed, and the efficiency was around 37 and 18% efficiency. And that's pretty simple why. It's these antennas are not meant to be used at 2 frequency because they are resonant elements, and that's why you have an efficiency much lower at downlink and higher at uplink. That's the reason why. So because we're much more efficient, our antenna is smaller, the beam is larger, and the mass is much, much, much smaller. So the fact that the beam is larger allows us to have less stringent requirement on the pointing. So we'll have a big gimbal pointing toward Earth, but because our antenna is much more efficient, the pointing requirement is relaxed. So that's another reason why it was very attractive. And the mass goes down by almost a factor of 2 to 2.5 compared to other technology. So that was a significant improvement. So then we went and said, okay, now that we've demonstrated that the subarrays work, we need to show that we can indeed maintain the efficiency with an array of subarrays. And the subarrays are, the array of subarrays are excited by, are fed by waveguide. Waveguide at X-band are not lossy, so we are not going to impact the efficiency. And we still got about 75% at uplink and 81% at downlink with the first prototype that we fabricated. We tested this antenna from -70C to 110C without any issue. We met all the requirements. And we were extremely happy. We also did radiation testing to make sure that we were not susceptible to IESD, electrostatic discharge, internal electrostatic discharge, and TID, which is total ionizing dose. And so we passed all these tests very successfully, and it's not by chance. So the way we actually designed this antenna was to make sure that every single piece of hardware, of material that we used to assemble this antenna was DC grounded. So the patch is held in place with a post, which is transparent from an RF point of view because the current flowing through this post is close to 0. But this post allows us to DC ground the patch elements to the ground of the antenna itself. And that's the reason why we don't have any issues with IEEE. And obviously, the final antenna is much larger. You can actually see it here on the lander, how it folds, how it deploys, and you can see the gimbal as well. So that's the concept and how it looks like. This is the final antenna. As you can see, it's a very pretty antenna. And the measurement as well, a very good agreement between calculated and measurements. So we're very, very excited. We're getting close to achieve TRL6. The last thing that we need to do is to perform a radiation pattern measurement at cryogenic temperature. We already passed all the vibration and acoustic tests. So we're moving forward to achieve TRL6, and then this antenna will be ready when we're ready to perform such a mission. And as you can see here, I wanted to see this picture that was actually taken only a few days ago. This picture shows how the lander looks like, and actually shows you the actual landing legs that's being developed also at JPL, which is very, very, very critical for this mission because we don't really know how the ice topography will look like. So we need to be able to land on any type of surface. And we have a team of mechanical engineers working on these landing legs that will allow us to do that. So as you can see here, how the legs are being laid out is to show that it could actually land on any topography on the surface of Europa. That's very exciting. There is many technology that being developed at JPL. Maybe one day I could show more of that. The team at JPL is very excited about this mission. So we're hoping that it would go from a mission concept to a funded mission, fully funded mission in the near future. But that's also an example of what I wanted to show you, is that to enable a mission, you have a lot of people developing new technology to enable this mission. So that's really what needs to be done all the time. It's very beautiful to see different fields moving forward together to enable a mission like that. That would be historical for the entire humanity. Okay, now I would like to talk about an Earth science mission that I am spending most of my time these last few years. It's called Surface Water and Ocean Topography. This mission is actually a very exciting mission that has an altimeter, a radiometer, an X-band telecom, and it has also a different instrument that allows us to know the attitude of the spacecraft and the orientation of the spacecraft very reliably. Here I would like to talk about the X-band telecom, which is what I contributed to maybe 5-6 years ago on this mission. It was very tricky because we have a K-band interferometer that needs a very good phase stability. We could not use a high gain antenna with a gimbal to achieve high data rate communication. So as a result, we had to use a low gain antenna to achieve high data rate communication, which is not typical. So as a result, one way to do that was to do a frequency reuse. So we use one single antenna with two different polarization, left and right at the same time, that do not interfere from each other, to multiply the data rate by 2. But it's pretty tricky because since we're using a low gain antenna, you are very susceptible to multipass on the surface of the nadir deck, and especially more since you have this large reflector that can focus this reflected power coming from the low gain antenna. So we had to design a low gain antennas that had very good cross-polarization discrimination, and especially so off-bore side at 60 degrees, because that's when most of the data will be transmitted. So that was quite atypical requirements. And we also needed a very rapid roll-off at 60 degrees, after 60 degrees, to make sure that we don't have a lot of reflections coming from a multipass on the nadir deck. So we developed this externally corrugated horn that allows us to do that, that covers the 8 to 8.45 gigahertz band. And as you can see, this is the pattern that we obtained. So at 60 gigahertz, we made sure that we had a very good cross-polarization discrimination, so we could still communicate at this angle fairly well. And we had about 7 dBi at this angle. So here it's normalized. I should have written that somewhere. Those are normalized pattern. And the XPD here, like I say, is very important. You can see that at 60 degrees, we are at 25 dB XPD, which is quite outstanding. Those are numbers that you get from a deep space network at bore site, and we're getting these values at off-bore site, which is very difficult, across a very wide frequency band. And so then, once you do that, you need to verify that it still works on the spacecraft. And here you can see the grasp model of the spacecraft, where we have the all the instruments. We have the nadir deck, We have the Nadir altimeter, the LRA, DORIS, NIMR, the radiometer. And we verified that the XPD over temperature is still meeting the requirement that we had. And as you can see, that's the case. The requirement shows in a dashed line. And we obtain very, very good results. And hopefully we will get very good data once we fly this spacecraft. So just wanted to show you where we're at right now. This is actually the payload. My antenna is here, but it's covered with a hat that allows us to measure in a non-control environment like this, the performance of the X-band telecom. You can see the Nadir altimeter here, and you can see the radiometer here. This mission is a collaboration between CNES, France, Space Agency, and NASA. And so some of the instruments like Nadir altimeter and DORIS were delivered by France, and we're delivering the payload, and we're also delivering, as part of the payload, the carrying instrument, the interferometer operating at K-band. And this is the video I'm showing you here. We're deploying the boom, and then we're deploying the reflector array. And here we have two feeds, one at V and one at H, with H polarization, that illuminates this reflector array that you will see in a deployed configuration. And CNES is also delivering the bus of the spacecraft with the solar arrays. And so as you can see here, the spacecraft is in fully deployed configuration. On the paper, a reflector array antenna like that can sound pretty trivial, but it's not. The mechanical deployment is absolutely outstanding, and the stability, the reproducibility of the deployment is very, very difficult to achieve because we're looking at some milli-degrees of phase stability. So it's actually quite outstanding. And same for the pointing. The pointing requirements are very, very important because you have two antennas, one because it's an interferometer, and the co-alignment between these beams is very, very important for the instruments. Okay, I think I'm running out of time, so I'm going to skip the Mars helicopter. Maybe I'll show you a few key things. For the Mars helicopter, we developed the telecommunication system on the rover side and on the helicopter side. So we have a monopole on the solar panels. You can see it here. That's actually the flight hardware. A few things that we had to be very careful about is the impact of the solar blades. The impact of the blades on the radiation pattern of this antenna. And as you can see, as the blades rotate, it's impacting the polarization of the antenna itself. So that, depending on where you end up here, where the blades are located when you're landed, you will see that the performance of your link will be impacted. And that's what I've been looking at, and that was part of my job as the telecom system engineer, and also as the antenna Kogi delivering these antennas. So that's on the rover side, where we have a monopole in very bad location because that was part of the accommodation. They couldn't accommodate other location that would have been better in terms of performance for us. But we had to live with very, very bad performance of the antenna. And that's the assessment that we made. So when we are landed on the floor, those are the performance that we get. So we can achieve 250 kilobits per second in the dark green spots, and we can achieve 20 kilobits per second in the light green spots here. And the inner circle is about 250 meter diameter, and the outer circle is about 1 kilometer. We expect that most of the communication will occur in this inner circle. And in the worst case, you can see that sometimes we might not be able to close the link, but the likelihood of being in the worst case is very low. And even if we end up being, it's like less than 92% likelihood. And if we end up being here, all we have to do is change the orientation of the blade to make sure that we are not in this worst case scenario again. So those are all the analyses to make this operation constraints recommendation to the operation team. And when we fly, we don't have any problem at all, as you can see, because we don't have any multipass with the ground. Things are fairly good. So we went into the field and we actually did a field test where we had a mock-up of the rover and we had the helicopter antenna on the other side. So obviously we didn't test in this configuration, but we tested when we had a separation, I think, of about 250 meters, and those are the predicts and the measurements. So the predicts, you can see that we were never in the worst case scenario, which would be the curve on the bottom. And we actually ended up even being better than the ideal case that we calculated, which is not surprising because when we do link budget, we have a lot of worst case assumptions. So this is exactly what we would like to see. So that was a very successful test. Okay, then I'm just going to conclude by telling you about this cool project that we just initiated. So this concept is to look at whether we can use a crater on the moon to make a telescope that could get some very, very good science. Since we will be on the other side of Earth, we will be able to only look at the emissions that we're interested in, which is the signal from the dark ages. And we are going to be completely shielded from emissions from Earth. And so, as you can see, these two reflectors that we have on Earth are the biggest one on Arecibo, 300 meters, and FAST, which is the Chinese telescope, which is 500 meters. And in our case, we're trying to achieve a 1 kilometer reflector. So what we're looking at is much lower frequency. So we're looking at what type of mesh we can use to meet the science requirements and what type of feed we need to meet the science requirement as well. And that's what we just started. I'm very excited about this mission concept, and I hope that I will have more to share with you guys in the future. Okay, just to conclude, here are a bunch of publications that I invite you to look at. So you can find all of that on IEEE. And there is a lot of good resources on things that I've been discussing about earlier. And also, I have a book coming up very soon. You can find it on pre-order on different sites, including Amazon. So if you're interested, don't hesitate. And I'm more than happy to sign a version if I see you in person. Okay, I'm open for any question now. Thank you for everyone's attention.
Okay, thank you, Nacer, and good luck for your upcoming book. Now I am opening the dais for questions. Actually, Nacer has on so many interesting projects. Now I am opening the dais for several questions from the audience. If you have any questions, please.
I would like to ask as to why no, instead of reflector arrays, which is quite complicated, we could have gone for a simple waveguide arrays, because at Ka-band, the sizes are very small. And it is an extremely efficient one if you use a waveguide array. So why that option is never considered in any of the missions, antenna designs which you have done.
When you say waveguide array, are you asking about slot arrays?
No, not necessarily. Waveguide element arrays. So, elements, each element is a waveguide. And at Ka-band, they are very tiny. And you can even make so to make them lighter.
So like open-ended waveguide?
Yeah.
Is that what you have in mind? Okay,
yes.
But open-ended waveguide are always going to be larger than what we're being using here. That's going to take much more volume. You cannot have something that extremely flat, and all the panels that we're flying, they are not even that thickness. It's much thinner than that, so they can fold against the CubeSat. So if you're looking at open-ended waveguide array, you're going to take too much time. Slot arrays are much more an option, but still at K-band, because you need to have power divided that are made of waveguide, it's going to take too much space. So it's not going to be as compact as what we're using. So only the feed is considered as being a horn or a slot array or anything like that. But for the panels, we cannot do that. It's taking too much thickness.
Yeah, that is true. That is maybe because of serious engineering considerations, you might have done that. But it's a reasonably elegant solution if you can slightly afford the weight.
I didn't hear
because
the last
the losses are very less, because the arrays, the main problem is the loss. See, if you see that reflect arrays, out of 52 dB which we have thought, you have brought down to almost 3 dB less and got only 48. I mean,
sorry, you're talking about the reflector array, right? You're talking about the reflector array.
Yeah.
Yeah, you're talking about the reflector array. I agree with you that at K band, but it's one thing you need to understand. Let me show you, because obviously, so one difference between academic and some of the work we do is that we have realistic constraints, and I'll show you what are the realistic constraints in this case, which are really driven the losses that we have. So on this deployable array, the constraints here are very, very, very important. So first, we have the sub reflector that needs to fit here, and it cannot exceed that. So this size only allows you to eliminate the reflector in a certain way. So if you go with a very large reflector array like that, you're also constrained by how you can eliminate it with a subreflector like that. And if I could have made this subreflector bigger, I could have minimized the spillover losses on this reflector. So those are the kind of trade-off that we deal with. I do think that at K-band, this is not the ideal concept, but this is the only concept that is compatible with the 6U CubeSats. So if you can live with this performance, this efficiency performance, with a 6U CubeSat, then it's still very, very attractive. So you always need to look at the different trade-offs that you have. So now the K-band, if you're looking for performance and you don't have any storage constraints or size of the CubeSat, you can use that. That one is almost 70% efficiency or 60% efficiency at K-band. So those are the trade-offs you always need to work with. And actually, you know, if you want to learn a little bit more about the trade-off and the recommendation that I myself took the liberty to make, I invite you to look at this publication, which is what is it? This one. So here is a review, Advanced CubeSat Antennas for Deep Space and Earth Science Missions, where I actually explain how we decide what type of antennas to use for CubeSat, depending on the constraint that we have.
Thank you. Thank you very much.
Thank you for the question.
Is there any more question from any side?
Hello, sir. I have one question.
Yeah, let us have, please.
Sir, can I design an antenna which provide any type polarization according to situation?
Okay.
Sorry, I did not understand what you say.
So do you want to ask, like, you want to have antenna on board, linear, circular, LHCP, RHCP, or anything? Is this your question?
Yes, sir. Yes. Which provide any type of polarization according to the situation.
Okay. So actually, Nacer, he is asking that can we have polarization reconfigurable such type of antennas?
Such as what?
Polarization reconfigurable. Such type of reflector.
With which antenna? With which antenna?
With any of the reflector antenna on board with CubeSats.
Let's see. If you wanted to have a linear, horizontal, and vertical, for example, and switch from one to another, is that the question, for example?
Yeah.
Okay. Yeah, so that's totally feasible. And even if you wanted to do a circular right or left, that's also not too difficult to achieve. Because the reflector array itself, you can develop reflector array that are don't really care about the incident polarization, right? So for example, the Marco one reacts the same way to circular polarization or linear, whether it's horizontal or vertical. So you need to achieve that with the feed. So you can, there is a lot of publication that shows you how to generate a feed that switch from linear to horizontal. It's not that difficult to do that. And you can do that with 2 different ports, for example. You can have the same feed with 2 different ports that gets, if you excite one port, you get vertical, or the other port horizontal. So that's very simple to do that this way.
Yes. So, so by this, I think we may stop for question answer session. If anyone still have questions, you can email on the contact email, whatever we have provided. We will directly contact with Nacer on the same. By this, I would like to first of all thank Nacer to discuss this many types of missions with the audience. And now I would like to invite Dr. Ankit Dubey for just a minute of vote of thanks.
Thank you, Dr. Amit. So I would like to first of all thank the speaker, Dr. Nacer, who has presented his work, which are, you can say this is the constraint-based work, as it has come while having the questionnaire discussion. Like there is a, yes, so now we are also understanding there is a gap between academia and industry, or you can say the agencies who are working actually on the ground. So basically, we have to keep this constraint in mind as well while we are designing. So I would like to also thank the those who mentioned this thing and the fact which has come out of this. So this is the beauty of this interaction. Like when you are interacting, when you are having such talks, then there are certain questions which are coming into your mind, and then it is getting resolved on the spot. So so it was a very wonderful talk. And I would like to also thank all the participants who enthusiastically attended this talk, and also who are having several questions in their mind. So it has ignited, and it has started the process of thinking and towards the engineering, the new design, and towards the working towards the antenna side for the satellite. So I also have one question. So with thanks, I have a question for Nacer, that could you please tell us, like, let's say our team at IIT Jammu is also working to develop a CUBE satellite. So what is your suggestion for us? Like, what should we focus more on so that we can have a technology which is very recent and which is very, you could say, which will fit into our future?
Yeah, so first, the number one advice I would give is make sure that it's not only an RF effort, and you need to work with a mechanical team, because as soon as you work on CubeSat, you will be involved with probably deployments. If you don't have to deploy, then don't deploy, because it's adding risk. So if there is no rationale to have a larger aperture, just stick with the easiest. And the things that I would recommend to look at in terms of antenna technology would be there are you need fundamental things like UHF antennas if you're going to have a low Earth orbit, a CubeSat, probably S-band antennas. And do not restrict you only to high gain antennas. You also need low gain antennas for short range communication. If you're doing science in low Earth orbit, you will need high gain antennas. And then you will want to look at reflector array technologies. You would want to look at slot arrays as well if you're looking at higher frequencies. Mesh reflector, I would say, if you have local collaboration with companies that are working with mesh reflector, that would be a good thing to do because they are very attractive. So I wouldn't focus on only one technology. You need to first have a trade-off to see what is the best solution for you, and then move forward to push for this technology. But there are simple things that needs to be done, which I don't think have been done yet in India for CubeSat. So you can also focus on that, like low gain antennas that could be commercialized very, very quickly, because as soon as you will have commercial companies flying CubeSat, I'm sure ISRO is going to start doing more of CubeSat. They will be looking for these type of technologies as well. So there is a lot of things to do. So I really invite you to look at this review paper that I have right there, this one, because you will get a lot of information there on what is the spectrum of things that you need for CubeSat in general. But then you also need to work with radar experts. If you want to do good science, work with radar experts that will allow you to develop technology that shrink the radar as much as possible, like we did for RAINCUBE, and those are the things that you have to do.
Okay, thank you so much for enlightening us with this such a wonderful this discussion. And I would also like to thank all the participants and all the attendees who attended this talk. So now I would like to also at the end, last but not the least, the organizers for Dr. Amit and his team. So thank you so much. So I would like to give control back to Dr. Amit and proceed with the event. Thank you, Nacer.
Welcome.
So Dr. Nacer, actually at IIT Jammu, we are working from lower Earth orbit microsats for go into maybe extended up to deep space. So as of now, we are thinking about real-time imaging, maybe by using ISAR technology, and later on we may extend for other applications as well. So this is just a view that how we are working for. And maybe in future, I will of course contact you regarding many such kind of problems related to our such project, and we'll be happy if you can suggest us sometimes, depending on our requirements.
Yep.
Yeah. So by this, I think now the time is to wind up. So for Nacer, very good morning, very good day, and for all of you who were in India and in this region, good night, and we'll meet you again with very excellent and exciting session. And the session
Thank you for organizing.
This session was also live on YouTube and will be available for the participants later on also. Okay, thank you. Good